Okay, so we're in chapter 3. You may recall that in chapter 1, we studied energy conservation. Energy conservation. While in chapter 2, we studied modes of heat transfer, like Fourier's law. What we will do in chapter 3 is put these two together to come up with a very general equation for energy transfer that we call the governing equation for heat transfer. The good thing about this is we're not going to derive this kind of equation every chapter. We're going to derive it once, and for half the class, we're going to keep using this same equation over and over again. So it's very important. Okay, so the contents of this chapter, we're going to talk about the governing equations, as we said, and then we'll also see that governing equation, to solve them, we need boundary conditions. So we're going to talk about governing equation and boundary conditions. We start with Cartesian, that is the simplest, and then we also do cylindrical, and then finally we do an adaptation for tissue. That includes the effect of blood flow. For boundary condition, we're going to talk about the many different types. Now, this overall energy balance that we did, where we could define any sort of control volume, and we say the amount of energy coming in and the amount of energy going out, with the amount of energy generated in the control volume, they are related by this statement of energy conservation: in minus out plus generation equal to change in storage. This was quite useful. It's a statement of the second law of thermodynamics. However, you notice that when we did this problem, there was only one temperature. When we did these problems, we had only one temperature for the entire domain. Now, you know, in most systems, temperature is going to vary from one location to another, and the heat flow is going to vary from one location to another. It could be more here, less here, or other way around. This information, the variation with location, is not going to be available in the kind of analysis that only has energy conservation. So we need more information. So we need the Fourier's law that we already talked about. That will provide us how heat flow or temperatures vary from one location to another. So we will get back to the control volume or the energy conservation analysis again, but this time with more details. And to be able to do those details, we have to define one quantity, that is how much thermal energy is there in a flowing mass. So to start with, we know that in a mass m, the amount of thermal energy, or the enthalpy, is m times Cp times its temperature T minus some reference temperature. Okay, and so that's the amount of energy that's there in a mass, and its unit is joules. Now we want to know how much energy is there in a flowing mass. So in a flowing mass, in the same way, energy can be defined as not mass, but a mass flow rate, m dot, so that we talk in terms of a flowing mass, otherwise it's the same. So the unit becomes joules per second. And what is this m dot? So let's think of an area A through which we have a mass uh, flowing. Okay, so if u is the velocity, then of fluid flowing through this, then of course u times area is the volumetric flow rate, and so that times rho is the mass flow rate. So this mass flow rate is really written in terms of velocity, area, density, and the rest of it stays the same. So what we would need later on is not energy amount but energy flux. So energy flux, if you recall, flux is always defined as energy per unit area. So if you divide this quantity by area, then you get this. What does that mean? So if there's fluid flowing through this area A continuously, so more keeps coming, okay, how much energy is it carrying through this area per unit area? That's given by this quantity. So we're going to see that this is really energy flux due to bulk flow, due to simply because the fluid is moving into and through this area, it's carrying this much energy with it. Okay, we are now back doing the same kind of energy conservation analysis, except that we're going to do this considering the modes of heat transfer. So this is going to be more detailed than the energy conservation that we did before. So we choose a small volume fixed in space. So this could be a small volume inside the room, air, or it could be a small volume in the body tissue. The point is, it is a small volume in an arbitrary location that's fixed in space. So through this control volume, things can go in and out, and energy can go in and out. Okay, and so this is the enlarged version of that control volume, and the size of it is delta x this way, delta y, and delta z. And now, as I said, we bring in the modes of heat transfer, meaning how energy can get into this control volume and get out of this control volume by different modes. So the first one is we want to consider conduction. So you remember from Fourier's law, conductive heat flux is given by minus k del T del x. So if this is my location x and this is my location x plus delta x, then the conductive heat flux at the location x is given by this quantity whose units are watts per meter square. So this is how much watts that are entering this phase, whose area is of course delta y times delta z here, and this is the amount of energy that's entering per unit area, not over the entire area but per unit area. And the amount that is going out would be written symbolically the same, minus k del T del x. This is my Fourier's law again, and but evaluated at this point. So the temperature gradient can be different at that location. The other way, and so by the way, what is the nature of this? So if we think of, if this is room air, so at this point, maybe the temperatures are a little bit warmer than here. And these molecules, the air molecules, they're bouncing against each other. So the warm molecules, when they collide into colder, it's going to impart some energy. That is the nature, that is what is captured by this minus k del t del x. So that is the mode of conduction, or the mechanism of conduction. Now, another way energy can come into this control volume is not because of conduction, but simply because air flows into it. Because air has some energy with it, if it flows in, it carries some energy. That's what we just did in last slide. And we know the flux for that. We just derived this. So this is the flux, again in watts per meter square, of energy coming into this control volume simply due to bulk flow. And because these things like temperature, like velocity, we are allowing things to vary, so we, in order to get the energy flux due to bulk flow, we need this quantity evaluated at x. So once again, this is on top of how energy is moving in by conduction. This is simply because the air itself is moving in. Now, if it cannot just move in, it also has to get out, otherwise it's going to pressurize and there will be an explosion, right? So it also has to get out. So energy flux, again, at this end would be symbolically written the same way, but uh, evaluated at x plus delta x. So now we got both the modes, energy flux due to conduction, energy flux due to flow. So together they make up the total flux. And the same this way. Now this same volume can have heat generation. What is an example of heat generation? If this is tissue, then this could be metabolic. If this is air, of course, there is no other source of heat generation, but we're not doing this for air or tissue. We're doing for arbitrary system. So there could be other chemical reactions going on inside that would generate heat. And so if this is a piece of food, for example, this is, that you put in microwave oven, then the water molecules in this is going to generate uh, heat by absorbing the electromagnetic energy of the microwaves. So that would be another item that we have to consider in the energy balance. Okay, using the fluxes that we defined, we are going to now do the details of the energy balance on a control volume. So this is my control volume. Again, remind you the size is delta x this way, delta y this way, and delta z this way. So let's go through the details now. All we are going to do is use energy conservation. So back to our in minus out plus generation equal to change in storage, change in storage over this volume that is fixed in space. So this volume can be in a fluid, like, at some corner in your classroom, in the air, or it could be a volume that's in some part of your body, in the tissue. So this could all be, the material could be the tissue. We just want to do a standard heat balance on this piece of tissue. Um, so how does energy come into this control volume? So notice one thing, that there's only two ways energy can come in. One is the conduction, which is given by minus k del t del x. And let's just keep the relationship to the physics always in mind. What is meant by conductive movement of energy? So if there are molecules here, if this is a gas, if there are molecules here on this side and there are molecules here, on the surface of this, some warmer molecule will bounce into the colder molecule, and therefore it's going to give some extra energy. So this random or diffusive movement of the molecules is going to lead to this conductive heat transfer. So this is just that part. Then there is another part, and the other part has to do with bulk flow. So if this is your classroom, for example, and I have a fixed location in space, then air can go in and out. And that's what this part is. So this air, as it moves in, it brings some energy with it. And that's the energy due to bulk flow. And that energy, which is kind of hard to see here, which is what we derived, it's U rho Cp times T minus Tr. We just derived that. So that the unit for this is again joules per meter square per second. So watts per meter square, or flux, is simply due to the air moving into this control volume through this phase, the phase here. Okay. So then how do I write how much energy goes into this control volume over time delta T? Notice the unit for this one is also joules per meter square per second. Okay. So to see how much energy went into through this control volume, this one, we have to then multiply by the area. So this is my flux, joules per meter square per second, times this is the area of this phase. This phase, which is same as this phase, which is delta y, delta z. So times meter square and times a second. Okay. So then this is the amount in joules of energy that went into this control volume through the mechanisms of conduction and flow. And we just saw the part due to conduction, and let's make sure we also have the flow. So this is my flux of energy due to flow. And so that's how much energy is coming in because of the bulk movement of air. But that's per unit area, so it needs to be multiplied by area, which is so this is joules per meter square per second, and so this is meter square, and then this is seconds. So if these cancel, then we get joules again. So this is the joules that have been brought into this control volume over time delta T. Okay, and it's not just coming in, things can also go out. So energy can go out, again, the same two ways. One is diffusive or conductive, and the other is by bulk flow. Again, the same term.
but the term is evaluated at this point because it's going out. So this is x plus delta x. So it's going out, and this is also at x plus delta x. So the amount that goes out this phase, amount of energy that goes out this phase over time delta t is given by these two quantities. So this is my flux at that phase times the area. This is a mistake here. This is twice. This is the area in meter square and second, just like the in term. And then this is due to flow. And then again, this is being flux, this being flux, this is multiplied by area and time. So again, you see all of each one of these is joules. So this is the joules that goes out. So this in term that we calculated goes in here. The out term that we calculated goes in here. Now let's look at energy generated. Now, again, I want you to be really relating always to the physics. What is energy generation? A simple example of energy generation, if I chose this control volume inside a tissue, there could be metabolic heat generation Q inside that control, inside the tissue that's in the control volume. So I define energy generation as Q watts per meter cube, which is joules per meter cube per second. Okay, so that is the rate at which energy is being generated. So if I ask the question, how much is generated over the entire volume over time delta t, then it will be q multiplied by the volume multiplied by the time. So this is the energy generated. That is this other term. Now, finally, uh, all this because of what energy came in, what went out, plus what's generated, it's going to make a difference how much energy is inside there. It's going to have more energy, less energy. More energy means this place would raise its temperature. Less energy means it will have a lower temperature. So change in energy content of this mass is something that you already know. It is mCp delta T, mass of that volume times specific heat times delta T, and delta T being its change in temperature. So the unit for this is also joules. So everything is consistent. All the joules are consistent. And so mass, what is mass? Mass is volume. So this delta X, delta Y, delta Z are, it gives me the volume times the density of whatever is the material that is in there times its specific heat. So that gives me m times Cp and times delta T. So this is my change in storage term, and that goes in to here, change in storage. So in my next slide, we're going to plug in these four terms and then do some simplification. Okay, so we are going to now just complete the algebraic simplification. So you recall that this is the equation where we plugged everything in minus out plus generation equal to change in storage, and one of the terms, let's just take the conduction term. For in was minus k del t del x at x, and then minus at times delta y, delta z, delta t, right? And the other term was minus uh, out is minus k del t del x at x plus delta x times delta y delta z delta t. Okay, so I just want to take those two terms just to there's only limited space here, so you divide throughout by delta x delta y delta z delta t. Then what do you get here? This delta y, delta z, they go away, and you get left with a delta x in the denominator. So that's what this term is. Okay? That's what this term is. You do the same with the convective term that was there next to it, and then you get this term. Okay, this is nothing else but rearranging the terms and dividing by delta x, delta y, delta z, delta t. And then for heat generation you get this one, and for the change in storage we get rho Cp del T over del T. Now you shrink this volume. So remember, our goal was to get an equation that gives me variation from point to point. Okay? So I want to shrink this volume delta x, go to 0. In other words, I take the limit. So you take limit as delta x, delta y, delta z, and delta t go to 0. Then you notice something interesting. Here you have some function at x plus delta x, and minus the same function at x over delta x. So it's in the form f x plus delta x minus f of x over delta x, and we're taking the limit delta x goes to 0. So this is obviously del f del x. So I'm writing del x of the function, which is this minus k del t del. So in the limit, then this becomes this term, and then this one minus rho Cp is fine, and then again the function at x plus delta x and the function at x divided by delta x, so that must be the derivative of this. So that's the derivative. You notice one thing though, I have removed the tr because tr is a constant reference temperature, and so there's no need to keep that in there's no need to keep that inside the derivative, so we have dropped that. And then q is q, and then rho Cp del t in the limit of del t going to 0 becomes del t. Okay, so then further simplification and rearranging. So I bring this term to the right hand side, and this term also to the right hand side, whereas this guy I bring in to the left hand side, and then this also to the left hand side. So this is my final equation that really, it is really energy conservation. It's just a statement of energy conservation uh, that um, would give us temperature from one location to another location. Um, okay, So remember, this is not a math class, right? So just we derived an equation and then we just solved the equation. That's not exactly what we want to do in this engineering class, where we want to relate it to engineering quantities. We want to relate it to the physics. So every term of the equation that we have, we should be able to interpret them in physical terms. We don't want to be in math domain. So the equation, we can actually interpret each term this way. So the first term, if this rho Cp is a constant, then I can put it inside the derivative. So you see the t has been multiplied by rho Cp. And so what is the unit of rho Cp? You notice that rho Cpt is mCpt over V, because m over V is rho. So which means what? Rho Cpt is just energy. We know this energy content is joules. So then rho Cp, unit of that is joules per meter cube, right? So, and then we have a time unit in the denominator. So the unit for this term is joules per meter cube per second. So what is the meaning of that? It's the rate, because there's a time in here, rate of change of stored energy. Stored energy is joules per meter cube and rate of change of that. And the same way we have this term, and let's go through that. So again, rho CPT, as we just said, unit of that is joules per meter cube. U is the velocity with which things are moving, and that unit of that is meters per second. So if we cross out these, we get joules per meter square per second, and then this x also has a unit of meter. So then what do I get? We get joules per meter cube per second, which is same as this other guy, uh, but they have to be, because they're all part of the same equation. Um, so then this is the rate of energy change, because energy again is joules per meter cube. Rate of energy change due to flow, because of this velocity. You notice there's a velocity. So because of the velocity, this term represents energy that simply flows into the control volume. Energy that simply flows into the control volume. In the same way, if you do this term, its unit is also going to come as joules per meter cube per second, and we know this term is for conduction. So then this is rate of energy change due to conduction. And likewise, the last one is rate of energy generation. Remember, the unit for this is also watts per meter cube, which is joules per meter cube per second. Okay, so I want you to see that each term has a particular physical meaning that's very direct. That's all it represents. It just represents a particular physical process in the equation. Before we move on, I want to make one simplification. You notice that in the balance that we did, so if this is my delta x, then u velocity coming in has to be equal to u velocity that is going out, because we are talking about things that are not being compressed inside. We're not talking about things that are being compressed inside. So u times the cross-sectional area, u at, let's say, x, and this is x plus delta x. So u at x times the cross-sectional area, okay, that's the volumetric flow. That should be same as U at x plus delta x times A, because things are not being compressed, so that same uh, density also stays the same. So the same mass that goes into this uh, this uh, the in part of the control volume should be the same that's coming out. So because the areas are constant and we are saying density is constant, so this is for constant density systems. These are not for compressible cases. Then we have ux is equal to ux plus delta x. I can rewrite that as u at x plus x minus ux, and just is equal to 0. And because it's equal to 0, I can divide it by delta x. And then it is still equal to 0. And then if I take the limit, then what do I get? I get del u del x equal to 0. So this term we will use to simplify this guy, because this guy has two terms. So this guy has two terms, that's u del t del x plus t del u del x, right? We all remember that chain rule. So this has two terms, and this term, because of this being valid, this is 0. So this means u can come out, okay? It's not because u is a constant. It's more correct to think that we are talking about flow that is not compressible, and we are using up this equation. We are using up this equation which has a name. It is the continuity equation. So using this equation, we are simplifying this. So from now on, you will often see the convective term written as not ut inside, but something like this, rho cp u del t del x. Okay? So I don't want you to think that u is a constant, but it's because we have simplified it using another equation, del u del x, which is the equation of continuity. So the governing equation that we just derived, it has many terms. It looks kind of complicated. Um, it is simply a statement of conservation of energy that we want to use, but it's still kind of complex. So I want you to see that this is like the equation with the different terms is just like a toolbox. Toolbox has many tools. You don't need, for most of the cases, you don't need all of them simultaneously. So you take out the tool that you need for a job. This is how you want to see. But all the tools are there together. So that's exactly what the governing equation is. And what is the advantage of that? We have kept it very general. We didn't drop physics. So we have all the typical physics that we deal with. It's all there. So what you do, and because of that, we also did not do this for the air or for the tissue. It's for anything. It's for any material, any size or shape, and also we are going to soon do other coordinate systems. And then the beautiful aspect of this general governing equation approach is, just like here, you're always safe to carry this Swiss knife that has all the tools. You never know which one you're going to need. And so In case of the equation, you drop the terms that you don't need, but you're keeping a record of what you dropped. So you know why you dropped a particular term. So you know that physics you are ignoring. This is extremely helpful so that you don't get surprises. Ah, I forgot to consider that physics. Okay. But that equation, uh, it still has some, you know, simplifications, some assumptions. It can be made even more general, but we don't have to deal with that in this class. Okay, for example, one little thing we would do is the variable property. Remember how the term, the conduction heating term is sitting like this, okay? And so this K can be brought out. So if K is a constant, then this is just del square T del X square. So this we can do starting from the equation that we did there. Now in a live class, I actually ask this question to the class and give you a couple of minutes to think about. So after I'm done asking you the question, you should pause the video for a couple of minutes and think about my question and try to give the answer. So the questions are, the heat equation that we just derived, does it really apply to these two situations? Okay. One is a 3D complex geometry, as you can see, and the other is a 3D cylindrical geometry, but it has a solid part and a fluid part. Okay. And so now you can pause the video and take a couple minutes to try to answer that. This is extremely useful so that it forces us to think um, about what we have done so far and how it applies and its relationship to the real world. Okay, so now the answer. So this is a complex 3D geometry. Yes, the in the first answer, it will be hard to apply that equation because that equation is only a function of x. So t in the equation is a function of x. However, remember how we drew the control volume and we did energy flow this way? We could also do the other two directions, okay? And then we will get the 3D version of the equation. I actually saved you the trouble of not doing more algebra, but that equation, for example, the heat, the conduction term, that is K del square T del X square that I showed in the last slide, if it is for 3D, then it's going to look like K del square T del X square plus del square T del Y square plus del square T del Z square. Okay, so the equation that we derived, once it is extended to 3D situation, then yes, we can use it for heat conduction in this kind of a complex geometry. It's not, again, we are not going to do in this class, but analytical solutions are harder unless you simplify this to some simple uh, geometry. But conceptually, the equation that we derive, which is a statement of energy conservation, of course, can be applied to this somewhat odd shape. Okay. But getting solution is harder in the ways that we are going to do in this class. um, unless we simplify to some simple shape like a sphere. Okay, in this one, again, you have a solid domain and a fluid domain. So in the solid domain, of course, the one difficulty we're going to have is this equation is in Cartesian coordinate. So which works well if the geometry looks like that. But in this kind of a geometry, the equation is still valid. It's not wrong, but it's going to be hard to use it for a geometry like this and get a solution. So for this, we're going to derive a cylindrical version of this equation. And then, then after that, it will apply in the solid. Then for the fluid part, remember our equation has a velocity term. So yes, it the equation we have is applicable to the fluid domain as well, except that this domain will have a different property than this domain. So we'll have to use different properties for this domain, but it is applicable. The equation is that we derive is a statement of energy conservation. There's no reason it is not applicable, but it could be a real pain to try to use that to get a solution for a cylindrical geometry. So again, for the inside part also we need the equation in a cylindrical coordinate. Okay, so the term one, and we're going to go over the four terms. Okay, so term one represents change in storage. Do I need that term all the time? No. When do I keep it? It's a transient problem. Temperature is changing with time, and so if temperature is changing with time, then this term stays. When do I get rid of it? It's a steady state problem. So temperature does not change with time. So del T would be 0. Then we look at term 2. Term 2 is this one. Notice it has a velocity. So just to remind us that this term it has to do with flow. So when do I keep it? When there is a flow, like in a fluid. When do I get rid of it? So suppose we're talking about a solid with nothing flowing through it, no pores or any other ways of things flowing through a solid. So in a solid, we don't need this term in a non-porous solid. Okay. Then next is term 3. Term 3 is this one. We can remind ourselves what this is about. This has thermal conductivity. So this of course has to do with thermal conduction. Now conduction is automatic. As long, the molecules always have energy as long as they're above absolute zero. So heat conduction can always take place in a very passive way, unless of course every place has just one temperature. Somehow temperature is uniform everywhere. If the temperature is uniform, then del T del X is 0, del square T del X square would also be 0. Then finally, term 4, this guy has to do with heat generation. So anytime we have conversion of other forms of energy into heat. So let's think for a second. This term basically takes care of any other form of energy being converted any into thermal. So the way we are handling that is this equation is a balance of thermal energy. So if some other energy just gets converted into thermal energy, to us it's like, well, thermal energy seems to appear from nowhere. So we're going to put that in Q. Of course, energy cannot appear from nowhere. It has to be converted from another form. Okay. So the example, simple example. So in a tissue, for example, there will be metabolic heat generation. When you are heating food, then microwave or the electrical energy is being converted into thermal energy. In metabolism, chemical energy is being converted into thermal energy. When there's no such source, when there's no conversion of energy, then of course we can drop the Q term.